Let's evaluate a fairly simple looking triple integral. All the limits of integration, the boundaries are constants. We have an interior function, x plus y plus z, and the integration order is z is first, and then y and then x. So if z is the first variable, so to speak, that means x and y would be constants. And this would lead us to the following. Integral from 0 to 3, integral from 0 to 2, and then we would x times z plus y times z plus z squared over 2, dy dx come later, and then z's limits were from 0 to 1. All right, so that's where we are to start with. If z is 0, all three terms are 0. If z is 1, we would get 0 to 3, 0 to 2, 1x plus 1y plus 1 squared over 2 is 1/2. Dy dx. So now y is the variable. X and 1/2 are both constants. So we get x times y plus y squared divided by 2 plus 1/2 y. Later we'll do dx. And y's limits are from 0 to 2. If y is 0, all three terms are 0. If y is 2, we will get the following. 0 to 3, 2x, 2 squared is 4. 4 divided by 2 is 2. Half of 2 is 1. Otherwise known as 0 to 3, 2x plus 3 with respect to x. And last but not least, x is our one and only variable remaining. The antiderivative is x squared plus 3x. And the limits of integration are from x is 0 to x is 3. We will get 3 squared is 9. 3 times 3 is 9. 9 plus 9 is 18. Now, let's look at this a little differently. If that triple integral is 18, I wonder what possibly we could be measuring. We already have 3 dimensions here. Technically, this is a 4th dimension, and we're staying away from the science fiction interpretation at the moment. Time is sometimes another measurement we'll use. So let's look at the region briefly if we could. I don't want to hide it all. X, Y, Z. If the x boundaries go from 0 to 3, and the y boundaries go from 0 to 2, and the z boundaries go from 0 to 1, we would have this quite literal rectangular prism or box please apologize. I accept my apology for my picture here. It's a very, very rough sketch. This would be the region of integration, all right? This is our region of integration. If the x plus the y plus the z, the function inside, is our density function, then this could have been the mass of that solid object is 18, and whatever the units of measurement are, perhaps grams. This could have been mass. So, just a little bit of moving in the direction we're headed to visualize the triple integral, volume or physics measurements such as mass and moments are probably the easier types of computations to understand for right now. So I have a little follow-up question. If you had switched the order to dx, dz, dy, would this have changed anything about this integration? Dx, dz, dy. So I want you to hit pause and see if you can switch that order of integration and also evaluate it. So you should be paused for a few minutes here. And then what I'm going to do for you is show you that worked out after you come back from the pause. All right, I'm back. Since the boundaries are constants, you can switch them to any order you want in terms of the alphabetical order. So that would be the triple integral and dx, dy, dz. And if x is the first antiderivative, then it would take us to here. And then z would be the next antiderivative. Remember, you have a pause button. And that would take you to here. And then it simplifies. And finally takes you ultimately to the y antiderivative. And again, hit pause if you need to. Sure enough, 18 it is. Quite easily done.